Alright, so here we have a matrix and we have to check if it's Hermitian or unitary, right? So let's recall what Hermitian means. So we say that a matrix is Hermitian if the transpose conjugate of a matrix is equal to the matrix itself. And we say that a matrix is unitary if A star times A is equal to the identity. Remember that A star represents the transpose conjugate of A, right? So you take the transpose first and then the conjugate. Or you can equivalently take the conjugate first and then the transpose. It wouldn't make a difference, right? So let's quickly check what would be A star in this case. So that would be nothing but 1 minus I and then 1, right? Which is same as A. So we can say that the A is Hermitian. Now to check if A is unitary, you need to multiply A star with A. What will that be? That would be 1 minus I1 multiplied with 1 minus I1. That would be equal to 2 minus 2I, 2I and 2, right? So this is not equal to the identity matrix, right? So A is not a unitary matrix. Now the third option says all eigenvalues are real. This is the case for every Hermitian matrix. In fact, for all Hermitian or even for symmetric matrices, right? Symmetric real matrices, symmetric real. So either it is Hermitian with complex or symmetric real matrix, right? We can say that the eigenvalues are all real. Now, why does this hold? Because for that, let's say V is an eigenvector of the matrix A, right? Now consider. So what does that mean? That means AV is equal to lambda V, right? Again, V is a non-zero eigenvector. Now, if I multiply on the right by V star, so V star AV would be equal to V star lambda V, which is same as lambda V star V, right? Because lambda is a scalar, you can pull it outside, right? Now again, if I take the uh, transpose conjugate of this whole thing, I will get V star A star equal to, again, lambda is a scalar, so the transpose conjugate will just be the conjugate, lambda conjugate times V star. Now if I multiply on the right by V, I will get V star. Instead of A star, I'm writing A because A is Hermitian. V star into A into V is equal to lambda conjugate V star V, right? So now what we can observe is that this guy here is same as this guy here, right? So we can say that V star V times lambda minus lambda conjugate is equal to 1. Now since V star V is non-zero, because V is non-zero vector, we can say that lambda is equal to lambda conjugate. So a complex number when equal to the conjugate, that just means that lambda is a real number, right? So we can say that all the eigenvalues are real. Eigenvalues are complex. This is not true. We just showed that all eigenvalues are real. So here's the next question. So it seems we have to do the diagonalization of A, right? So let's start off. Let's first find the eigenvalues of A, right? So we need to solve, to find out the eigenvalues, we need to solve the determinant of A minus lambda I equal to 0, right? This is known as a characteristic equation. So when we solve this, we get 1 minus lambda whole square minus 1 is equal to 0. Now if we solve for lambda, we'll get lambda to be either 0 or 2, right? So 0 and 2 are the eigenvalues. Now we have to find the eigenvector corresponding to these eigenvalues. Let's start with lambda equal to 0. So we need to look at A minus 0 times I, which is nothing but A, right? So that would be 1 minus I1 multiplied with some vector V. So let me write V as V1, V2. This is equal to 0, 0. Right? Now we have to solve for V1 and V2. So from the first row, we'll get that V1 is equal to IV2. Now in the second row, we'll get that minus V1 is equal to minus IV2, right? So essentially both of them are the same, right? So we have one condition V1 equal to IV2, right? So what will be the eigenvector? So the eigenvector will be such that the second component can be anything. Let me call that T, but the first component has to be I times the second component. So this should be IT, right? Essentially, so this means that uh, this is spanned by, so the whole eigenspace, so the eigenspace of lambda equal to 0 is nothing but the span of IT, right? Oh, sorry, not IT, I1, right? So I1 is an eigenvector, right? Now, what is the norm of norm of the eigenvector I1? The norm would be under root 2, right? So, the normalized eigenvector will be equal to 1 by under root 2 I1, right? Now let's do the same thing for lambda equal to 2. So first we have to write a minus 2 times I, right? So what is a minus 2 times I? It will be minus 1 minus I and then minus 1, right? So this when multiplied with some vector v, so let me write that again as v1, v2, that should give us 0, 0. Right? Again, solving this, for the first row we get v1 is equal to minus I v2, and this is same as the second row also, right? So we have essentially one condition, right? So what will be the eigenvector? It will be having two components. The second component can be anything, right? Let me call that t, or let me straight away call that 1. And the first one has to be minus I times of that, right? So this is the eigenvector, right? Let me call that v2, or not v2. Let me call that w, right? So but again we have to normalize this, right? Because again the norm is equal to under root 2. So the normalized vector, normalized one is nothing but 1 1 by under root 2 times of minus I and then 1, right? So we have obtained both the eigenvectors, right, and the normalized ones. So these eigenvectors will form the column vectors of the first matrix, right? So we can write A to be equal to uh, minus I by under root 2, right, and then 1 by under root 2, I by under root 2, 1 by under root 2, right? And so for the first column vector, the eigenvalue is 0, so we'll write 0, 2, sorry, the eigenvalue is 2, and for the second one it's 0, so we write 2, 0, 0, 0, and then the transpose of this guy. So if I call this as Q, this is Q transpose, right? So the first option is correct. Again, notice that here it says A square, right? So if I write A to be Q D, where D is a diagonal matrix, Q D Q transpose, then A square is nothing but Q D Q transpose, again a Q, again a D, and again a Q transpose. Now, since Q is an orthogonal matrix, Q transpose Q is identity. So I can write this as Q times diagonal squared times Q transpose, right? And this is exactly what is given here. So this is Q, right? This is Q transpose, and this is the square of the diagonal matrix, which is this is D, right? So again, this is correct. Now I1 is an eigenvector of A. This is also true because we've observed that here that I1 is an eigenvector. In fact, any multiple of I1, so alpha I1, right, where alpha is any real number or any complex number, this will remain to be an eigenvector of A, right? So this is also correct. The last option says A is not diagonalized. This is definitely false because we just diagonalized it, right? This is false. Alright, so here we have a matrix, and the first option says that A transpose A is equal to something. So let's compute A transpose A. So A transpose A will be equal to 2, 1, 0, 1, 0, 1 multiplied by 2, 1, 1, 0, 0, 1, right? Now this will be equal to 5, 2, 2, 2. So the option is wrong because it has a 3, right? Then it says eigenvalues of A transpose A are 6 and 2, right? So we need to compute the eigenvalues of A transpose A. How would you do that? So we have to find the characteristic equations. The characteristic equation is given by A transpose A minus lambda I. Determinant should be equal to 0. So now if you solve for this, we'll get 5 minus lambda multiplied by 2 minus lambda minus 4 will be equal to 0. Now this means that we have lambda square minus 7 lambda plus 6 equal to 0, right? So this means lambda minus 6 times lambda minus 1 is equal to 0. So the eigenvalues are 1 and 6, right? Right. Okay. So we've obtained so it's 6 and so the option says 6 and 2, so the option is 4. Then it says an eigenvector of A transpose A corresponding to the eigenvalue 6 is 2 comma 1, right? So to find out the eigenvector, right, what we have to do is that we have to solve the equation A transpose A into V is what we have to find, that is equal to lambda into V. What is lambda here? 6. So 6 into V. So that is A transpose A minus 6i times V is equal to 0. This is what we have to solve. So what is A transpose A minus 6i? A transpose A minus 6i is equal to, or multiplied by V is equal to minus 1, 2, 2 and minus 4. This is multiplied by, let me write V to be V1, V2 equal to 0, 0, right? So from the first row we can say minus V1 plus 2 times of V2 is equal to 0, which means that V1 should be equal to 2 times of V2. From the second row we can say that 2v1 minus 4v2 is equal to 0. That means v1 is equal to 2v2 again. It's the same condition. Right? So essentially we have only one condition which says v1 is equal to 2v2. So the eigenvector corresponding to lambda is equal to 6 is given by, see, v1 can be anything, right? Sorry, v2. So we can choose one of them to be anything. Let me choose v2 to be 1. Then v1 has to be 2 times of v2, which means it should be 2, right? So this is an eigenvalue. Also, whenever so this is an eigenvector. So whenever we say an eigenvector, we use the word an instead of the, because if you use the eigenvector, that means the eigenvector is unique, which is definitely not the case. Because if v is an eigenvector, then you multiply v with any scalar alpha, right? Alpha v will also be an eigenvector, right? So it's never unique. Okay. In fact, if you multiply the eigenvector to 1 by, say for example, you multiply it by 1 by under root 5, right? This is again an eigenvector. And why would we do this? Because sometimes we want to normalize the eigenvector, right? We want the eigenvector to have a unit length, okay? So the next option says the orthonormalized eigenvectors are, okay, so we already found out the eigenvector corresponding to lambda equal to 6. So now let's do the same thing for lambda equal to 1. So A transpose A minus 1 times I into V is equal to 0. This is what we have to solve. So this will be nothing but 4 2 2 1 multiplied by V1 V2 equal to 0 0. Right? So from this we can say that 4 times V1 plus 2 times V2 is 0, which means that V2 can be written as negative 2 times of V1. So now again we have to select the eigenvector corresponding to lambda is equal to 1. That will be equal to, see, v1, let's choose v1 to be 1 and v2 should be negative 2 times of v1, so this should be minus 2, right? So again the norm of this eigenvector is under root of 5, so we divide it, so we will normalize it and we will write it as 1 by under root 5 1 minus 2, right? Again observe that in the second eigenvector which is given here, the minus is in the first component and there is no minus in the second component. Now this doesn't matter, right? Because we can always multiply. So multiply by minus 1, right? What will you obtain? Minus 1 by under root 5 and 2 by under root 5. Again this is the last option is correct. Because whenever you multiply the eigenvector by a scalar, it remains an eigenvector. Okay, so in this question we have that A can be written as Q1 into sigma into Q2 transpose, right? So what is Q1? Q1 will be the So A is of size 3 cross 2, right? Q1 will be of size 3 cross 3, sigma will be of size 3 cross 2, and Q2 transpose will be of size 2 cross 3. Sorry, 2 cross 2, right? Because Q2 is also of size 2 cross 2, right? Now, and what will be the values in sigma? So sigma will contain value. So sigma will contain values which are under root lambda 1, under root lambda 2, and so on, where lambda i's are the eigenvalues of A transpose A. So this is what we know. So from here we can say that, so we've obtained the eigenvalue of A transpose A to be 6 and 1, right? So from there we can say that sigma should be equal to the second option, not the first option, right? Now it also asks for Q2, right? So we know again that what is Q2. So Q2 will be the will be the matrix of orthogonal eigenvectors of A transpose A, right? So again, in the previous question, we have obtained the eigenvectors, and so the correct option is the second one. Sorry, the third one, the fourth.
Alright, so we have a quadratic function f of x1 comma x2, which is given by 2 times x1 square plus 7 times x2 square plus 12 times of x1 x2, right? So the matrix representation for this quadratic form will be such that the coefficient of the square terms, which are 2 and 7, will go into the leading diagonal, and the other two terms, right, it will not be 0, it will be such whatever the other two terms are, right, so the other two terms will sum up to 12. Why 12? Because 12 is the coefficient of x1 x2, right? So if you look at the options, the first option is satisfied, the second is not, the third is not, and the fourth is also not satisfied, right? So this is the correct answer. Now the next question says which of the following options are true. It actually asks us to see if A is a positive definite matrix or a negative definite matrix, or if it is neither, right? If it is neither a positive definite matrix nor a negative definite matrix, then we call it to be a indefinite matrix. But before doing that, let's look at the conditions for a 2 by 2 matrix to be positive definite. So let me write R1. So R1 are all the conditions for a 2 by 2 matrix to be a positive definite matrix. So the first condition is that A11 should be positive. And the second condition says that the determinant of the matrix should be positive. Let me also write R2 as the conditions for a 2 by 2 matrix to be negative definite. And in this case we have that A11 should be negative and the determinant of A should be positive. Now let's check it for the A in our question. The A in our question is 2, 6, 6 and 7. So A11 is 2, which is positive, and the determinant of A is nothing but 14 minus 36, which is negative. So we see that it neither satisfies R1 nor R2, which means that A is indefinite. That means the last option is.
Alright, so here we have a question on PCA. Although the question first asks us to compute the sample covariance matrix for the data set, right? So the data set is given by, let me denote it by x1, x2 and x3, right? And each xi belongs to R2, right? There are three data points, right? So what is the sample covariance matrix? So the sample covariance matrix C is given by 1 by n times, which is like the average of xc transpose, right? Now the question arises, what is xc, right? Xc denotes the uh, centered data points, right? So xc denotes the centered data points. Now what do I mean by centered data points? It means you take every data point and subtract the mean of all the data points from that, right? How do we do that? We take, so what is x? X is the data matrix, which is nothing but x1, x2 in the second column and x3 in the third column, right? This is x. Xc on the other hand would be nothing but x1 minus mu, x2 minus mu and x3 minus mu as the first, second and the third columns respectively, right? So for this we need to first compute mu. And what is mu? Mu is nothing but 1/3 of x1 plus x2 plus x3. This is a simple average, right? Now this will be equal to 1/3 of 3, 3, 3, which is essentially 1, 1, 1, right? So what will xc be? Xc will be equal to not 3, 3, 3, it should be just 3, 3. There are only two, it's in R2, right? So the mu is also a member of R2, okay? So the first one would be minus 1, minus 1, minus 1, 1. The second one would be 1, 1, minus 1, 1. And the third one would be 3, 3, minus 1, 1. Right? So these are the columns, right? So the first column is minus 2, and then 0, 0, and then 2, 2. Right? So this is the centered matrix. Now let's go back and compute the sample covariance matrix, which is given by 1 by n. Instead of n, I'll write 1 by 3. And then xc. Xc is minus 2, 0, 0, 2, 2. And then xc transpose would be minus 2, 0, 0, 2, 2. Right? The transpose of that, right? Now this will be equal to 1 by 3 times of 4 plus 4, which is 8. Again 4 plus 4. So all of them are 8, right? So this is the sample covariance matrix for the particular data set. Alright, so the next question asks for the principal direction that is chosen for performing PCA. So typically in these kind of problems, we'll have to take the eigenvalues or the eigenvectors of the sample covariance matrix, and that eigenvector which corresponds to the largest eigenvalue will be the principal direction, right? So that is the technical, so that's the primary way of doing it. But since there are only 3 points and all of them are in R2, we can actually easily get a geometric interpretation of where the points are, right? So let me write R2. This is x1. So not x1, let me write x and then y, right? So where is minus 1 comma minus 1? It will lie somewhere here, right? So this is the point minus 1 comma minus 1. Now we need 1, 1, which is somewhere here. This is the point 1 comma 1. And the point 3 comma 3 will also be here. So essentially what we can notice is that all these 3 points, they lie on the same line, right? So they are collinear points, right? Collinear points, which means that they lie on the same line. Now what is the benefit of lying on the same line? It's just that, see, now where is the variance maximized? The variance will be maximized exactly where, exactly on this line, right? So what is this line? This line is nothing but y equals to x. This is the line, right? Now Since this is the line and the points are collinear, right? The projection of each point will be the point itself, right? So the projection of each point will be the point itself. In fact, so what is the principal direction that is chosen? It is along this line, right? Which means it is along the line W equals 1, 1, right? Or if you want to normalize it, so W normalized. So typically we normalize vectors, right? Because we want them, we want all of them to be a unit vector. So you can write this as 1 by root 2, 1 by root 2. So now in the next question we have that if x1 tilde, x2 tilde and x3 tilde are the projections of those data points onto the first principal component, then basically we have to find x1 tilde, x2 tilde and x3 tilde, right? Now see, we have already seen that they lie on the same line, and this green line here, right? So this is the first principal component, right? So this green line is the first principal component. Sometimes it is referred to as PC1, right? So it's PC1. So what will be the projection of these lines onto the line? It will be the points themselves, right? So the projections will be, so projection of any data point x, right, onto a line say W is given by, this is the definition of the projection, that you have to take the dot product of x and W. So let me write x transpose W and then multiply it with W, right? Now we are doing this assuming that W is a unit vector, which means the norm of W is equal to 1, right? So now let's do this. Let's do this for one data point, right? So projection of let's say the point 1, 1, right, onto W. So we saw that W is nothing but 1 by under root 2, 1 by under root 2, right? So W is equal to 1 by under root 2, 1 by under root 2, right? So this would be x transpose W. So x transpose W is nothing but 1, 1 written as a row multiplied by 1 by under root 2, 1 by under root 2. And then this is multiplied by the vector 1 by under root 2, 1 by under root 2. So this will be nothing but 2 by under root 2 multiplied by 1 by under root 2, 1 by under root 2, which is nothing but 1, 1. So observe that we got back the same vector, right? Similarly, you can see that the projection of the point 3, 3 onto W will be 3, 3, and the projection of -1, -1 onto W will also be equal to -1, -1, right? So essentially all the points are projected onto themselves. So the final answer would be that x1 tilde will be nothing but x1, which is nothing but -1, -1. Similarly, x2 tilde will be equal to 1, 1, and x3 tilde will be equal to 3, 3. This is the final answer. Alright, so here we have a question on a matrix, which is a 2 by 2 matrix, and then we are asked if it is positive definite or negative definite or semi-definite and so on, right? So there are several methods to solve this question. I think I have discussed one method, which is by looking at the leading cofactors, the determinant of the leading cofactors of the matrix. So let's adopt another way here. Let's use the method by computing the eigenvalues of A, right? Of A. So what does this method say? It says that if all eigenvalues are positive, so if all lambda I are strictly positive, then it is positive definite, right? And if it is not strictly positive, but some of them are 0, then it is positive semi-definite. Similarly, if all of them are strictly negative, we call it negative definite. And If some of them are 0, then we call it negative semi-definite. So we can write the characteristic equation of A in order to find the eigenvalues of A, right? So characteristic equation of A will be nothing but the determinant of A minus lambda I set to 0, right? That will be nothing but 3 minus lambda, 2 minus 2, and then minus 1 minus lambda. Determinant set to 0, which I can write as negative of 3 minus lambda, 1 plus lambda, uh, plus 4 equal to 0, right? Now I can write this as minus of minus lambda square minus plus 2 lambda and then plus 3 plus 4 equal to 0. So I can rewrite this as lambda square minus 2 lambda plus 1 equal to 0. That means lambda is plus minus 1, right? Not plus minus 1, sorry. Lambda is 1, right? Lambda is plus 1, just plus. There's only one root, okay? So since all there is only one root, but this appears twice, which means the algebraic multiplicity of this eigenvalue is 2, right? So we often write it as 1 comma 1, right? So this is the set of eigenvalues, and both of them are strictly positive, right? Strictly positive. So what we can say is that it's A is positive definite using this particular criteria, right? So using this criteria, we can say that A is positive definite.
Alright, so here we have a question on gradient descent. Consider a function fxy which is given using gradient descent algorithm with an initial guess of 3, 2. This means that x0 is nothing but 3 and y0 is nothing but 2, right? And the learning rate is actually dependent on t, which denotes the iteration, right? So the learning rate, let me denote it by eta. Eta t is nothing but 1 by t plus 1, right? The question says what will be the value of xy after 2 iterations, right? So what does an iteration look like? So we say that using gradient descent xt comma yt, right? This is the new point. This will be assigned the value which is the difference between the uh, t minus 1th, let me write this as t minus 1, t minus 1, yt minus 1, which denotes the previous data points, minus eta t times the gradient of f evaluated at xt minus 1 and yt minus 1, right? This is the gradient descent algorithm, right? And this update happens starting with the initial point 3, 2, right? Okay, so let's do this for the function given in the question. So the first iteration would be in the first iteration what will we have? We will have that x1 y1 will be written as x0 y0, which is nothing but 3 2 minus eta t would be, this would be eta of uh, 1, which is uh, 1 by 1 plus 1, right? So 1 by 1 plus 1 times of the gradient of f. So let's also find out the gradient. So the gradient of f is nothing but 2x minus 4 and 2, right? So this is the gradient. So we have the gradient, so we need the gradient of f, right? And this should be evaluated at the point x equal to 3 and y equal to 2. That's what we want, right? So this can be rewritten as 3 2 minus 1 by 2 times of, okay, so the gradient of f is 2x minus 4 and 2, right? So 2x minus 4 will be nothing but 6 minus 4, which is 2. So 2 comma 2, right? Now this will therefore result in the vector 2 comma 1, right? So this is the value after the first iteration. Now we'll have to do one more iteration, which is the second iteration. And what happens there? We didn't we compute x2 and y2. And how do we do that? By the same methodology, we look at the previous data point, right? x1 and y1. x1 and y1 minus eta of t will now be 1 by 2 plus 1 times the gradient of f. The gradient of f is 2x minus 4 and 2, and then we have to put here x equal to x1 and y equal to y1. Okay? This is the gradient descent algorithm. Now this can be rewritten as 2 1 minus 1 by 3 times, so this is minus 1 by 3 times of, this would be 0 and 2, that would be equal to 2 1 by 3, right? So this is the final, so this is the data point or the value of xy. So xy after 2 iteration will be nothing but equal to 2 comma 1 by 3, right? So the answer is the last option, x is 2, y is 0.33. Alright, so here we have an optimization problem actually, right? So the question says find the points on the circle x square equal to 4 plus y square equal to 4 plus x square. So this is definitely, so first of all, this is not a circle, okay? This is not the equation of a circle. So the equation of a circle typically is of the form x square plus y square equals to r square, right? This is the equation of the circle. And what is given in the question is an equation of a hyperbola. In fact, if you plot this, it will look something like this, right? So this is the graph, okay? This is definitely not a circle, okay? But let's go with the question closest to the point 3 comma 0, right? So essentially what we have to do, let me rewrite this problem in the form of minimization of, so what we want to do, we want to minimize the distance between a point, an arbitrary point, and the point 3 comma 0, right? So what is the distance between an arbitrary point and 3 comma 0? It's nothing but x minus 3 square plus y minus 0 square, right? Now this is the function that we want to minimize, but subject to, we have a few conditions. What is that condition? The condition is that y square minus x square minus 4 should be equal to 0, right? Because we want those points to lie on this particular hyperbola, right? So now first thing I have to do, let me denote this function as f and this as g equal to 0, right? So f is a function of x and y, g is a function of x and y, right? Okay, what is, so this, we will solve this by the method of Lagrangian multipliers, right? So what does the Lagrangian multiplier method say? It says first equate gradient of f to be equal to some constant L times gradient of g, right? And then what we have to do, and then solve for L, x and y, right, using this equation which is given above, and you also have to use the fact that g of x comma y is equal to 0, right? Here what is g of x comma y? It's nothing but y square minus x square minus 4, okay? So this is the method of Lagrangian multipliers, Lagrangian multiplier method, right? So if you want a video on why this makes sense and the logic and the proofs behind Lagrangian multiplier method, let me know in the comments down below, okay? Right, so before starting off, notice one thing. So if we do gradient f equal to L gradient g, right, what will we have? We will have x and y as variables. Additionally, we will have L also as a variable, right? So we have 3 variables, right? And how many equations do we have? We have 3 equations, right? Because grad f equal to L times grad g will give us 2 equations, and one equation is nothing but gxy equal to 0. So essentially this problem is solving 3 variable 3 equation problem, right? So which can be solved, okay? Now let's go about it. What is the gradient of f? The gradient of f is nothing but 2x minus 6 and 2y. Okay, so this is the gradient of f. Okay, now what is the gradient of g? The gradient of g is minus 2x and 2y. Okay, and we have to set grad f equal to L times of grad g, right? So now let's solve this. So first we have 2x minus 6 equals minus 2lx, right? And then we have 2y equals to L into 2y, right? So from the second equation, this one, we can say that if y is non-zero, right? If y is non-zero, then L will be equal to 1, right? Because we can cancel two y's, right? Right? So let me take a case. Case 1. What is case 1? Case 1 is that y is non-zero. Okay? Y is non-zero. If y is non-zero, then we can immediately say that L is equal to 1, right? But when L is equal to 1, we can put that here in this equation and say that that implies 2x minus 6 will be equal to minus 2x, which will mean that x is equal to 3 by 2, right? So we get this thing, that x is equal to 3 by 2. Okay, but what will y be? To find out y, we have to put this in gx equal to gx comma y equal to 0. So put this in gxy equal to 0. So what will we get? Y square is equal to x square plus 4, right? X square plus 4, and x square is 3 by 2, so 9 by 4 plus 4, which will be equal to 9 plus 16 by 4, which is 25 by 4, 25 by 4, that is equal to, so y can be plus minus, so that means that y can be plus minus 5 by 2, right? So we got the value of x, we got the value of y, right? But now what? Now we have another case to deal with. What if y is equal to 0, right? That is a case which we did not see. If y is equal to 0, right, then look at the gxy, right? So gxy will be equal to 0 square minus x square minus 4, right? But this can never be 0, right? Because x square is a positive quantity, minus 4 is a positive quantity, so this will always be strictly less than 0, right? So the constraint will not hold. So the constraint cannot hold. In fact, this actually means that y has to be equal to non-zero. Okay, so the only solution we have as of now is that x is 3 by 2 and y is 5 by 2. This is one solution. Another one is 3 by 2 and minus 5 by 2, right? Now in case of this, what we do, we compute the value of f. So f of 1.5 comma 2.5 is nothing but, this will turn out to be what? This will turn out to be 9 by 4 plus 25 by 4, right? That will be 34 by 4. Similarly, if I compute f of 1.5 comma minus 2.5, that will also give me 34 by 4, right? So essentially, both the second one and the third one are correct. Okay, I think in the answer only the second one is given, right? But again, that's a mistake and it has been corrected after some time. Alright, so here we have a question on Taylor's theorem, right? So it says the value of a function at a point f is and at a point 5 is 10, which means, let me write it as uh, f of 5 is equal to 10, right? The values of the function's first and second order derivatives at this point are 5 and 2 respectively. What does that mean? That means f prime at 5 is 5 and f double prime at 5 is 2, right? And what will be the function's approximate value at the point 5.1, right? So what does Taylor's theorem say? Let me write that. Taylor's theorem of approximation, right? it says that you take any function f, right? And if you want to know the value at a point which is little bit away from x, okay, so h is a value which is typically very small, okay, then you can approximate it as fx plus, right, h times f prime of x plus h square by 2 factorial times f double prime of x, and this goes on till h to the power r by r factorial f derivative r times on x, right? So as you increase r, your approximation will get closer and closer to the actual value. That is the idea of this theorem, right? So typically h is very small, right? This is very small, right? And we use it in conditions where we already know fx, f prime x, f double prime x, and so on, right? So in our question, we are given only the first and the second derivatives, so we will compute only till here, okay? So let's do that. So f of, what is x here? X is nothing but 5, because f of 5 is the value that we already know, right? So f of 5 plus 0.1, what will that be equal to? That is nothing but f of 5 plus 0.1 times f prime of 5 plus 0.1 whole square by 2 factorial multiplied by f double prime of 5, right? So this is like not equal, but it's an approximated value, right? Let me write approximated value. And what is f5? f5 is 10. What is, so what will this be? This will be 0.1 times 5, right? And this will be 0.01 by 2 times 2, right? So ultimately we have 10 plus 0.5 plus 0.01, which is 10.51. This is the answer to the question.